Okay, welcome. Let's talk about doing regressions other than just linear ones. So we're going to use data about iPhones that will be sold, and we're looking at the different models, the year after the year 2000, so 7 years after would be 2007, etc., and how many units were sold in terms of millions. So the first thing we're going to want to do is go into Staplet.com and create a scatter plot. And the year will be the explanatory variable. The units sold will be the response. And you're going to be entering the year or the units sold, just these numbers, not with the millions attached to it. And then you'll go ahead and sketch this out. Okay, when you're in Staplet, the option you're using is two quantitative variables, collaborative, I believe it is. It's about the fourth one down. And so we'll sketch it there. Yeah, two quantitative variables, collaborative. And now we're trying to decide, is linear a good model for this data? It looks fairly linear, but remember the way we find out is to look at the residual plot. So if you choose a regression method and choose least squares regression line, it will give you a residual plot on Staplet. And when we look at our plot from Staplet, we have this sort of curve shape. So because it has a pattern, a leftover U-shaped pattern, a linear model is not appropriate to use. And again, here's my graph, just so I have it handy. And any points above mean that the actual value is higher than the predicted, whereas below they were less than the predicted value. So now we need to use a different model, and we are going to transform the data. So what we've got to kind of do is look at this and say, what kind of transformation do we want to do? Well, in this case, oops, sorry for moving that around. It looks like our data was exponential. And if we remember, the simplest form of an exponential equation is of the form y equals a times b raised to the x power. And the way we undo an exponential function is the inverse of it, which is a logarithm. Now, it's been a while probably since you've looked at logs and exponents, probably Algebra 2. But here's some simple rules of how we transform our data. So if we had this equation, y equals a times b to the x, I'm going to take the log of both sides. So log of y equals the log of a times b to the x. Okay, nothing wrong with that. Now, by my properties of logs, if I am taking the log of two things that are multiplied together, I can separate them into the log of the first value plus the log of the second value. Another property of logs is that if you have an exponent in something you're taking the log of, that exponent can move down in front and be a coefficient of your log. So now I've got log of a, which is just some number, plus x times some number, which is the log of b. So I've got log of y equals the log of a, that's my y-intercept, plus x times the log of b. b represents our slope. So now my data will be transformed. So let's take a look at the next page here. And on this next page, we're going to complete this table. Again, I encourage you to do this work yourselves. I'm still going to have explanatory variable being the year, but instead of the response variable being actual units sold, I'm going to take the log of all of these values. So log of 0.5, and I get negative 0.301. Log of 1, and I get 0, etc. And once I've gotten these, I'm going to go back to my Staplet, same option, and I'm going to put in year again as my explanatory variable, and the log of units sold as the response variable. And we're going to take a look at our graph there and make a scatter plot. Oops, you can't see mine. So here is my very rough scatter plot. Again, you want to try and get it as accurate as possible, just for your own notes. But this time it looks a little bit better. So we've created our scatter plot here. And I can, again, get my least squares regression line by doing the regression method, least squares regression line. And we have to remember that the equation that I get, y hat equals negative 1.5356 plus 0.1828x, that represents the log of y. Okay, it's not y anymore because remember, our response value is the log of it. So I have to make sure I don't forget to put that log in. And when I write the equation, I can write it like this, but I would have to state what y hat represents and what x represents. Another way of doing that would be saying the log of units sold with a little hat or big hat over that equals negative 1.54, I just rounded there, plus 0.18x. And instead of x, I could put years after 2000. But somewhere I've got to get that context in there. Okay, so now if we were trying to decide was this a good fit or not, we're going to have to look at our residual plot. And if we look at the residual plot, there is no pattern. So is the linear model a good fit for the transformed data? Yes, because the residual plot shows no leftover pattern. There's an even scatter of points above and below the axis, so we are good there. Okay, now how do we use this? Well, according to this model, we want to see how many phones will be sold in the year 2015. So 15 is going to be my X value that I'm going to use to predict the number of iPhones sold. So I have log of my units sold equals negative 1.54 plus 0.18 times 15, because again, that's my explanatory variable. This over here just gives me a number, and that number was, sorry how messy that is, 1.16. So the log of my units sold equals 1.16. To undo the log, I have to raise 10 to this power and then raise this side 10 to this power. So I have 10 raised to the power of log of units sold equals 10 raised to the power of 1.16. Now 10 and log, because that's log base 10, will cancel with each other, leaving just units sold. And we get 14.45 million iPhones is what we would predict. And that kind of looks like it if you look back at our scatter plot up here. I could believe that. Okay, now we want to calculate and interpret the residual for the actual number of iPhones sold. Well, residual is the actual value minus the predicted. The actual was 13. And again, we've got that from our table right here. So 13 minus 14.45 gives me a negative 1.45. Now, if the residual is negative, that means the actual number of iPhones sold in 2015 was 1.45 below the predicted value. And that's how we would interpret it. Okay, let's just sum up the notes on the back now. And here are the key points from today's notes. Is different types of function. We could have a linear function. If so, then we're plotting x versus y on the graph. If we have a power function, then we will be plotting the log of x versus the log of y, and we have not done one of those. Or we could have an exponential, in which case we plot x versus the log of y. Now our predictions. To make a prediction when we have these different types, we take our x value and plug it in to solve for y. But we may need to undo a root or a log in order to get y. So if we're a power function, we'll have to undo a root. If it was exponential, we'll have to undo a log. And remember, to undo a log, we're going to take 10 raised to that log on both sides of the equation. When we do that, we end up with the simple value of y on the left equals 10 raised to the power of y plus b times x. Other functions and common ways to undo them, if you have the natural log, so ln, to undo that you're going to have e raised to some power. Instead of 10 raised to the power, it's going to be e raised to the power. For a common power one, if you have y to the third, so that would be a cubic equation, to undo that you take the third root, is how we undo it. We have a check for understanding here, and on my notes I have the filled in answer so you can see that. But again, the important thing here is how to read this mini tab output. Next to the constant is where you find your y-intercept. Next to your explanatory variable is where you find the slope. Your r-squared value, your standard deviation of the residuals is the s value. But I'm given these y-intercept and the slope, so I can go ahead and write my least squares regression line. And in the problem, it tells us that x is the height cubed. So y hat equals 45.08, my y-intercept, plus 10.809 times x, where x represents the height cubed. If I want to fill a box that is 8 feet high, then I need to plug in 8 feet cubed into my equation. So I would have 45 plus 10.809 times 8 to the third power, which gives me 5,579.216 balloons. It is important that we continue to leave the decimal places there, even though we know that we can't have parts of balloons. And the reason for that is when you're making a prediction, it will not be an integer typically. So to show that this is the predicted value, we leave those decimals. The actual value would be a whole number. Okay, the homework over this is section 3.3. Go ahead and read through that and then work on the homework. Have a good day.